Hello, my beautiful scholars. Oh, that was a little creepy. Okay, so let's review periodic trends. We're also going to talk about phases, which we talked a little bit in Unit 1. Both of these are going to be really important as part of Unit 3. So here we go. Periodic trends review. So the trends of atomic radius, ionization energy, electronegativity are important in chemistry and worthy of review. So atomic radius, I know that's the size. Ionization energy, that's like how hard it is to remove an electron. And electronegativity has to do with attracting electrons. Atomic radius is largest in the bottom left corner and smallest in the top right corner of the periodic table. Electronegativity and ionization energy have the opposite pattern. Okay. Electronegativity and ionization energy are the highest in the top right and lowest in the bottom left. So then if you look at the diagram, which is on your page, basically it's saying that if I do atomic radius in red here, because it's in red on here, atomic radius is big right here. So this is big atomic radius, and small atomic radius here. So this diagonal basically going from small to big. So like if we looked at these four right here, sodium would be the largest because it's the most to the bottom left. Okay, and then electronegativity and ionization energy, it said have the opposite pattern, so this would be high electronegativity, ionization energy, and this would be low ionization energy and atomic radius. And that's going the opposite way. Opposite ways. They just can't get along. So then if we looked at this one again, the most electronegative atom we would predict to be beryllium, because it's the most to the top right. Okay, let's keep reading. These trends occur due to differences in the number of protons. Okay, I know protons, those are the positive centers in the nucleus. And electron shells of atoms. To the right in a period, so to the right, all atoms have the same number of electron shells. Okay, but have more protons. The increased number of protons attracts electrons more strongly, increasing electronegativity. Okay, so more protons in the center, more positives, positive, 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 positive. The negatives get pulled in more. That makes sense? There's more positives. Since electrons are strongly attracted, they're more difficult to remove, and the ionization energy increases. Also seems reasonable. If they're attracted more, it's going to be harder to take away. So more attracted, more difficult to remove. The stronger pull also brings the valence electrons closer, decreasing the size. So if the electrons move closer, the size will be smaller. Okay, so that's for a period. So basically, to summarize, a period has to do with protons. That seems to be the main driving factor there. Down a group, so now this is vertical, the change in protons is less important than the change in the number of electron shells. Okay, here I'm going to box that. So electron shells is my focus here. The number of electron shells increases down a group on the periodic table. Whereas we said in a period, they don't change. But down a group, the periods are changing, so the electron shells are changing. With more electron shells, the valence electrons are farther away from the nucleus. Okay, so let's see. If we had the nucleus here, we have one shell, and then boom, we add another shell. Makes sense. They're farther away from the nucleus. Since the electrons are farther away, they're less attracted. Oh, wait, did I skip something? The atomic radius increases. Okay. They're less attracted to the nucleus, and electronegativity decreases. So if they're farther away, they're less attracted. Right? So Distance makes them not as attractive. It's like two magnets. If you hold magnets close together, they attract. If you hold them far apart, they still attract, but you can barely even feel it. Because the electrons are not attracted as strongly, they're easier to remove, so the ionization energy is lower. Okay, very good, very good. What's this last paragraph on this page? The radius of an ion, an atom that has gained or lost an electron, is also important. So an ion is an atom that has gained or lost an electron. Cations are smaller than their parent because they've lost electrons. Remember, cations are positive ions. The T looks like a positive. The protons are better able to attract the remaining electrons, so they get smaller. Anions, which are negative, are larger than their parent atoms because they've gained electrons. The protons are not able to attract the remaining electrons as well because there's so many electrons. Okay, so that's our periodic trend reading. Now you're going to have to go down to find the phases of matter reading. So, phases of matter. The three main states of matter, I guess states of matter is the same thing as a phase, are gases, liquids, and solids. The main difference between each phase is the degree, so basically like the amount of random molecular motion that occurs. Random molecular motion means that there's no set pattern to the way the molecules moves. The way the molecules in a solid, liquid, or gas move, they just move randomly. Molecules in a solid may vibrate but tend to retain their overall structure until enough heat energy is added to break the forces holding them together. Okay, so to melt, you've got to break those forces. Liquids have more random molecular motion, but not as much as gases, which have the most. So I'm assuming to go from liquid to gases, you have to add even more heat. Or energy. I'll write energy. How much the particles move is connected to how strong the attractive forces between the particles are. Okay, gotta read that again. So how much the particles move, is connected to how strong the attractive forces are. Okay, I'm gonna have to read this. These forces are called intermolecular forces. Okay, so these are intermolecular forces. In a solid, the intermolecular forces are very strong. Okay, so this is strong, I'll just say IMF, intermolecular force. So solids keep their shape and have a set volume. Okay, so here it has a set shape and it's not expanding or anything. Liquids have no set arrangement, so no shape here. But they do have a set volume, so it's not filling the container. Gases have very weak intermolecular forces. Is that the right spelling of weak? I don't know. And so do not have a set shape or volume and will expand to fill the container. So this is weak intermolecular force. And it expands to fill the container. Okay, be ready to discuss key points. So you might want to take a little time and write down some key points. And I'll see you in class, you beautiful, delicious people, you. Bye-bye.